So the next question is about acceleration, and we see this little scenario where there's a van and it's dropping 1 drop of oil every second. And it says the diagram shows the oil drops left on the road. So it asks us to describe the motion of the van in these 3 situations. So between W and X. So what we see is between W and X, the oil drops are getting closer together. So the distance between them is becoming less. So the distance traveled every second becomes less. And remember, distance traveled in a certain time is what we call speed. So this means the speed is decreasing, so we have negative acceleration or deceleration. Between X and Y, the distance doesn't change, so the distance is not changing with time, which means that we're traveling at constant speed. Between Y and Z, here the distance every second is increasing, which means that the speed is increasing, so we have acceleration. The next question is simply a calculation question. We're told that the van's driven for 20 seconds at this speed, calculate the distance, and we always use the 4-step approach. So the time is 20 seconds, the speed is 30 meters per second. We're looking for the distance. Distance is equal to speed times time. Notice that for distance we use the symbol S, not D. S is equal to 30 multiplied by 20, which gives me the distance is 600 meters. In the second question, it tells us the van was traveling at 30 meters per second and then slows to a stop. And this is important, the fact that they say slows to a stop. And it tells us this happens in 12 seconds. Calculate the acceleration. So what information we're told? We're told that initially its speed is 30 meters per second. We use the letter U usually for the initial speed. Its final speed is 0 because it slowed to a stop. The time was 12 seconds. The equation is acceleration is equal to the change in speed. So the final speed, take away the start speed, divided by the time. So the acceleration is 0 minus 30 divided by 12. So the acceleration is equal to minus 2.5 meters per second squared. Minus 2.5 meters per second squared. The minus means that the speed is decreasing. We have negative acceleration, otherwise known as deceleration. There's another of these checklists. In this case, the checklist is looking at the topics to do with forces by themselves, not related to motion. This is pages 201 to 204 in the revision guide. So let's take a look at those questions. So this first question tells us that there are horizontal forces acting on a man swimming in the sea. Describe the motion of the man when the resultant horizontal force is 0. So because there is no resultant force, that means there's no acceleration, so the man is moving at constant velocity. It then says the man increases force A. Explain what happens to force B and the movement of the man. So there are 4 marks for this question, so we need to have 4 relevant points. So the first sentence here I've written here is really just for me to understand what's happening. So when the force A is increased, now there's going to be a resultant horizontal force. Before, force A and force B were the same, so there was no overall force. Force A is increased, that means we're going to get an overall resultant force forwards. So this will cause the man to accelerate, and that will be my first point, first mark for talking about the movement of the man. As he moves faster, the drag force B will increase. This is my second mark telling me about what happens to force B. Eventually, force B will equal force A, so the resultant force will be 0 newtons again. Again, this is about force B, and that's my third mark. So the man moves at higher constant speed, which is going to be again about the movement of the man, and that's my final 4th mark. So a difficult question to get all the marks. You don't have to write in sentences, but you do need to put down the relevant bullet points. Now, the next part of this question is probably the most difficult question for people to answer in the forces topic, and it's about what are called vector diagrams, working out what is the size of a resultant force. Now, it's important to know the difference between a vector diagram versus what we call a free body diagram. Okay. So a free body diagram looks like this. A free body diagram is where we draw all the forces on an object. So here, for example, I might show the boat just as a box with boat written in it. I've got a 3,000 Newton force to the west and a 1,000 Newton force south. I could even just show it as a dot. 3,000 Newtons west, 1,000 Newtons south. So all the forces are coming from the same point. They're coming from the object. In a vector diagram, this is not what we draw. We draw the forces tip to tail, one after another. So let's see what that looks like. So the first thing to draw my vector diagram is I start with any of the forces. For example, I might start with the 3,000 Newton force west, and I pick a scale and I draw that force. Okay, so I've said that 6 of the big boxes correspond to 3,000 Newtons. So one of the little squares is 100 Newtons. Okay, so I drew that force first of all. I then draw the second force, but I don't draw it at the same point as I started the 3,000 Newtons. I draw it where the 3,000 Newtons ended. So I draw it where the first force ended, down like this. Okay, so now I've drawn all my forces are drawn. What I do then is I draw the resultant force from the start of the first force, the 3,000 Newton one, to the end of the last force, the 1,000 Newton ones, like this. This is my resultant force. So this is saying a force of this size in this direction is the same as having a 3,000 Newton force that way and a 1,000 Newton force downwards, and that's the same. What I can then do is I can measure the length of this line and use my scale to work out the size, or I could use Pythagoras' theorem in this case to work out the size of this line. I also have to measure this angle to find its direction, so you must have a protractor with you in the exam. And I find that my answer is 3,160 Newtons, and I've written here 19 degrees to horizontal, or I could have measured the angle from north and given it as a bearing. The second part of this, or the last part of this question I should say, is it says the force to the south on the boat increases. What effect does this have on the resultant force on the boat? Okay, and to answer this question, I decided I'm going to use my diagram. So what we're saying is, instead of having 1,000 Newton, I'm going to make this force larger. So I'm going to double it. So the force now goes all the way down to the bottom. That means that my resultant force line would be like this. And we can see that this line is bigger than the original green one. So that means my resultant force is going to be larger. So that will be my first point. It makes the magnitude, which means the size of the resultant force, larger. But we can also see that this angle is also going to increase. The resultant force is more towards the south, the downwards direction, than it was before. Previously, it was mostly to the west and a little bit to the south. Now it's more south. So I can say it changed the direction of the boat towards the south. So question 2 says that there are arrows on the diagram to represent the size and direction of forces on a space shuttle. The longer the arrow, the bigger the force. So they're saying that this is a free body diagram. So here we have our free body diagram, and we have the shuttle showing a large force upwards and a small force downwards. So the force up is greater than the force down. That means that there is a resultant force upwards. Describe the upward motion of the space shuttle 1 second after launch. Because there is a resultant force up, it will be accelerating upwards. Question 2 says, by the time it moves out of the Earth's atmosphere, Then weight of all the various bits has decreased, and so has air resistance. These are the forces downwards. So the force down is less, so that means the overall resultant force upwards is even greater. And because the resultant force is larger, it means that the acceleration will increase. Part B says the space shuttle takes 9 minutes to reach its orbital velocity of 8,100 meters per second. Write down the equation that links acceleration, change in velocity, and time taken. So this is the equation that acceleration is equal to change in velocity divided by time. And it says calculate in meters per second squared, so it tells us the units we need to use, the average acceleration of the space shuttle during the first 9 minutes of its flight. Show clearly how you work out your answer. So the start speed is 0 meters per second. It starts not moving. By the time it's reached the height after 9 minutes into orbit, it's at 8,100 meters per second. So the change in speed is 8,100 minus 0, which is 8,100 meters per second. That's how much the speed has changed. It's taken us 9 minutes to do that, but we have to change that into seconds, so that's 9 times 60, which is 540 seconds. Our equation is the change in speed over time. So it's going to be acceleration is equal to 8,100 divided by 540 seconds. So our acceleration is 15 meters per second squared. The average, this is not asking you to add things together and divide by some number. This is just saying that we are just using the start and end speeds to get how much the acceleration was between those 2 points. So we use this normal equation. Whenever they say average acceleration in this case, we're just using this equation. Acceleration equals change in speed divided by time. How is the velocity of an object different from the speed of an object? Velocity is a vector and speed is a scalar. It's really important in this type of question that you give both parts to this answer. If you say velocity is a vector and don't say that speed is a scalar, that will not get you a mark because you haven't said how it's different from speed. Because speed could be a vector as well, but it's not. You need to say velocity is a vector, speed is a scalar. Or if you said velocity has a magnitude and a direction, that's not enough. You need to then say that speed doesn't have a direction, it only has a magnitude. So you need to have both parts in an exam to get that mark. Okay, then we had question 3. It tells us force is a vector quantity. What does that mean? What's the correct statement about vector quantity? The correct statement, it has both direction and magnitude. Magnitude only is scalar. This doesn't mean anything, and that wouldn't mean anything either. So magnitude only is scalar. Vectors have direction and magnitude. It says a Newton meter measures the weight of an object. So what you need to do is work out where this arrow is pointing. It's between the 5 and the 6, so it's 5.5. Notice I write it as 5.5. I do not write it as 5.5. That is wrong. Next question is a pure calculation question, so we're going to follow our steps. It tells us the weight is 6.4 newtons. We're looking for the mass, and it tells us the value for gravitational field strength is 9.8 newtons per kilogram. The equation is weight is equal to mass times gravitational field strength. So I put in the number 6.4 is equal to mass times 9.8, and then I work out my calculation. I rearrange my equation to get mass is equal to 6.4 divided by 9.8, which gives me this answer. Mass equal to 0.65306122245 kilograms. That's what I get in my calculator. I now need to work out what do I need to write as the answer. How many decimal places should I have? So the question is, how many significant figures should I have in my answer? And the response to that question is the same as the numbers that were given in the question. 6.4, 2 significant figures. 9.8, 2 significant figures. So we write our answer to 2 significant figures. The last question, we're told that the mass of a bag of sugar is 1 kilogram. So that's 1 kilogram. On Earth, the weight on Earth is 10 newtons. And on Mars, the weight is 4 newtons. Okay? Suggest why the weight of the bag of sugar is different on Earth and on Mars. So weight is equal to mass times gravitational field strength. So for weight to be different, either the mass or the gravitational field strength needs to be different. Okay, so to change this value of W, I need to change either the M or the G, or both. Since mass doesn't change, because we haven't lost any of our sugar, this means the gravitational field strength on Mars is, well, it's going to be smaller, since the weight is smaller. How much times smaller? It's 10 divided by 4, which is equal to 2.5 times smaller than on Earth. Okay.